Section 1.1, Real Numbers. Algebra Essentials. Learning Objectives. In this section, you will 1. Classify a real number as a natural, whole, integer, rational, or irrational number. 2. Perform calculations using order of operations. 3. Use the following properties of real numbers: commutative, associative, distributive, inverse, and identity. 4. Evaluate algebraic expressions. 5. Simplify algebraic expressions. It is often said that mathematics is the language of science. If this is true, then an essential part of the language of mathematics is numbers. The earliest use of numbers occurred 100 centuries ago in the Middle East to count or enumerate items. Farmers, cattle herders, and traders used tokens, stones, or markers to signify a single quantity: a sheaf of grain, a head of livestock, or a fixed length of cloth, for example. Doing so made commerce possible, leading to improved communications and the spread of civilization. 3,000 to 4,000 years ago, Egyptians introduced fractions. They first used them to show reciprocals. Later, they used them to represent the amount when a quantity was divided into equal parts. But what if there were no cattle to trade or an entire crop of grain was lost in a flood? How could someone indicate the existence of nothing? From earliest times, people had thought of a base state while counting and used various symbols to represent this null condition. However, it was not until about the 5th century CE in India that 0 was added to the number system and used as a numeral in calculations. Clearly, there was also a need for numbers to represent loss or debt. In India, in the 7th century CE, negative numbers were used as solutions to mathematical equations and commercial debts. The opposites of the counting numbers expanded the number system even further. Because of the evolution of the number system, we can now perform complex calculations using these and other categories of real numbers. In this section, we will explore sets of numbers, calculations with different kinds of numbers, and the use of numbers in expressions. 1.1.1. Classifying a real number. The numbers we use for counting or enumerating items are the natural numbers: 1, 2, 3, 4, 5, and so on. We describe them in set notation as 1, 2, 3, dot, 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 where the ellipsis, dot, 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 indicates that the numbers continue to infinity. The natural numbers are, of course, also called the counting numbers. Any time we enumerate the members of a team, count the coins in a collection, or tally the trees in a grove, we are using the set of natural numbers. The set of whole numbers is the set of natural numbers plus 0, 0, 1, 2, 3, dot, dot, dot. The set of integers adds the opposites of the natural numbers to the set of whole numbers. Dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. It is useful to note that the set of integers is made up of 3 distinct subsets: negative integers, 0, and positive integers. In this sense, the positive integers are just the natural numbers. Another way to think about it is that the natural numbers are a subset of the integers. Negative integers. Dot, 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 -3, -2, -1. 0. 0. Positive integers. 1, 2, 3, dot, dot, dot. The set of rational numbers is written as m over n, where m and n are integers, and n is not equal to 0. Notice from the definition that rational numbers are fractions, or quotients, containing integers in both the numerator and the denominator is never 0. We can also see that every natural number, whole number, and integer is a rational number with a denominator of 1. Because they are fractions, any rational number can also be expressed in decimal form. Any rational number can be represented as either a terminating decimal, 15 over 8 equals 1.875, or b a repeating decimal, 4 over 11 equals 0.36363636 equals 0.36 bar. We use a line drawn over the repeating block of numbers instead of writing the group multiple times. Example 1. Writing integers as rational numbers. Write each of the following as a rational number. A. 7. B. O. C. -8. Solution. Write a fraction with the integer in the numerator and 1 in the denominator. A. 7 equals 7 over 1. B. 0 equals 0 over 1. C. -8 equals -8 over 1. Try it. Number 1. Write each of the following as a rational number. A. 11. B. 3. C. -4. Example 2. Identifying rational numbers. Write each of the following rational numbers as either a terminating or repeating decimal. A. -5 over 7. B. 15 over 5. C. 13 over 25. Solution. Write each fraction as a decimal by dividing the numerator by the denominator. A. -5 over 7 equals -0.7142885 bars, a repeating decimal. B. 15 over 5 equals 3, or 3.0, a terminating decimal. C. 13 over 25 equals 0.52, a terminating decimal. Try it. Number 2. Write each of the following rational numbers as either a terminating or repeating decimal. A. 68 over 17. B. 8 over 13. C. -17 over 20. A. Irrational numbers. At some point in the ancient past, someone discovered that not all numbers are rational numbers. A builder, for instance, may have found that the diagonal of a square with unit sides was not 2, or even 3, over 2, but was something else. Or a garment maker might have observed that the ratio of the circumference to the diameter of a roll of cloth was a little bit more than 3, but still not a rational number. Such numbers are said to be irrational because they cannot be written as fractions. These numbers make up the set of irrational numbers. Irrational numbers cannot be expressed as a fraction of two integers. It is impossible to describe this set of numbers by a single rule except to say that a number is irrational if it is not rational. So we write this as shown. The set of H, where H is not a rational number. Example 3. Differentiating rational and irrational numbers. Determine whether each of the following numbers is rational or irrational. If it is rational, determine whether it is a terminating or repeating decimal. A. Square root of 25. B. 33 over 9. C. Square root of 11. D. 17 over 34. E. 0.30333033333. Solution. A. Square root of 25. This can be simplified as square root of 25 equals 5. Therefore, square root of 25 is rational. B. 33 over 9. Because it is a fraction of integers, 33 over 9 is a rational number. Next, simplify and divide. 33 over 9 equals 11 over 3 equals 3.6 bars. So, 33 over 9 is rational and a repeating decimal. C. Square root of 11. This cannot be simplified any further. Therefore, square root of 11 is an irrational number. D. 17 over 34. Because it is a fraction of integers, 17 over 34 is a rational number. Simplify and divide. 17 over 34 equals 1 over 2 equals 0.5. So, 17 over 34 is rational and a terminating decimal. E 0.303303333333 is not a terminating decimal. Also note that there is no repeating pattern because the group of threes increases each time. Therefore it is neither a terminating nor a repeating decimal and, hence, not a rational number. It is an irrational number. Try it number 3. Determine whether each of the following numbers is rational or irrational. If it is rational, determine whether it is a terminating or repeating decimal. A. 7 over 77. B. Square root of 81. C. 4.27027002700027. D. 91 over 13. E. Square root of 39. B. Real numbers. Given any number n, we know that n is either rational or irrational. It cannot be both. The sets of rational and irrational numbers together make up the set of real numbers. As we saw with integers, the real numbers can be divided into three subsets: negative real numbers, 0, and positive real numbers. Each subset includes fractions, decimals, and irrational numbers according to their algebraic sign, plus or minus. 0 is considered neither positive nor negative. The real numbers can be visualized on a horizontal number line with an arbitrary point chosen as 0, with negative numbers to the left of 0 and positive numbers to the right of 0. A fixed unit distance is then used to mark off each integer, or other basic value, on either side of 0. Any real number corresponds to a unique position on the number line. The converse is also true. Each location on the number line corresponds to exactly one real number. This is known as a one-to-one correspondence. We refer to this as the real number line as shown in Figure 1. Figure 1, the real number line. Example 4. Classifying real numbers. Classify each number as either positive or negative and as either rational or irrational. Does the number lie to the left or the right of 0 on the number line? A. Negative 10 over 3. B. Square root of 5. C. Negative square root of 289. D. Negative 6 pi. E. 0.61538461538. Solution. A. Negative 10 over 3 is negative and rational. It lies to the left of 0 on the number line. B. Square root of 5 is positive and irrational. It lies to the right of 0. C. Negative square root of 289 equals negative square root of 17 squared equals negative 17 is negative and rational. It lies to the left of 0. D. Negative 6 pi is negative and irrational. It lies to the left of 0. E. 0.61538461538 is a repeating decimal, so it is rational and positive. It lies to the right of 0. Try it number 4. Classify each number as either positive or negative and as either rational or irrational. Does the number lie to the left or the right of 0 on the number line? A. Square root of 73. B. Negative 11.411411411. C. 47 over 19. D. Negative square root of 5 over 2. E. 6.210735. C. Sets of numbers as subsets. Beginning with the natural numbers, we have expanded each set to form a larger set, meaning that there is a subset relationship between the sets of numbers we have encountered so far. These relationships become more obvious when seen as a diagram, such as Figure 2. Figure 2 sets of numbers. N is the set of natural numbers. N equals 1, 2, 3, N. W is the set of whole numbers. W equals 0, 1, 2, 3, N. I is the set of integers. I equals -3, -2, -1, 0, 1, 2, 3, N. Q is the set of rational numbers. Q equals m over n, where n is not equal 0. Q's complement is the set of irrational numbers. Q's complement equals pi square root of 2, etc. Sets of numbers. The set of natural numbers includes the numbers used for counting. 1, 2, 3, The set of whole numbers is the set of natural numbers plus 0, 0, 1, 2, 3, The set of integers adds the negative natural numbers to the set of whole numbers. -3, -2, -1, 0, 1, 2, 3, The set of rational numbers includes fractions written as m over n, where m and n are integers, and n is not equal to 0. The set of irrational numbers is the set of numbers that are not rational, are non-repeating, and are non-terminating. It is the set of h, where h is not a rational number. Example 5. Differentiating the sets of numbers. Classify each number as being a natural number, n, whole number, w, integer, I, rational number, q, and or irrational number, q's complement. A. Square root of 36. B. 8 over 3. C. Square root of 73. D. -6. E. 3.21211211112. Solution. A. Square root of 36 equals 6. N, W, I, Q. B. 8 over 3 equals 2.6 bars. Q. C. Square root of 73. Q's complement. D. -6. I, Q. E. 3.21211211112. Q's complement. Try it number 5. Classify each number as being a natural number, n, whole number, w, integer, I, rational number, q, and or irrational number, q's complement. A. -35 over 7. B. O. C. Square root of 169. D. Square root of 24. E. 4.763763763.